going to talk for a minute about what I learned about bearing terminology when I was doing my research as to what kind of a bearing I want to put on here. We start with a crude drawing. Alright, so this is my shaft, and this is bearing as viewed from this direction as opposed to this direction. With me so far? Okay. So now let's pretend we turn this whole thing this way. So now we have the bearing. Let's pretend this circle is the shaft. In this case here, the shaft is rotating this way. And the forces that are being exerted on the bearing radiate, is a good way to think of it, a good way to remember it. They radiate outward from the center in this direction. Okay? The shaft is rotating, it's putting load on the bearing in this direction. The load radiates outward, the force radiates outward. So what they call that is they call it a radial load, as opposed to an axial load would be if this shaft, as it's rotating, has forces exerting on the bearing in this direction or both, back and forth. Okay? Now if you have a situation where you have very little radial load to worry about and you have a lot of axial load, like if this shaft was going into a housing with a blind hole, and you were worried about a lot of this type of force being put on that end, then what you would have in there would be what's called a thrust bearing to take that load. That would allow the shaft to rotate even if it's being pushed into a dead end, so to speak. For whatever reason, this pulley on the top, they designed it to use, I could put it away, but basically a big one of these, which is just a radial. This is what's called a deep groove ball bearing, and this is how most ball bearings are made. And this is made to primarily take a radial load and only a little bit of an axial load. Roller bearings, where instead of having balls inside here you have little cylinders of steel, are made for almost completely radial load and pretty much no axial load. Sometimes the designer will stack more than one bearing on top of another, and one might have the purpose of taking some axial load while the other might be there to take the brunt of the radial load. So you might have a roller bearing with a ball bearing behind it, or a roller bearing with a thrust bearing behind it if it's a closed end. For some reason, the bottom bearing in this particular application was designed in this way. It has this groove here, but it also has grooves, the upper and lower races here. So what this bearing is designed to do is this bearing is designed to be able to handle radial load and axial load. My problem is I can't figure out why. If I just completely forget about any axial loading on this, there's no reason why I can't put a regular ball bearing down inside here. I've already checked some sizes. I've got like 77 3/4 millimeters to play with in here. I could make a spacer, some type of a bushing, and put a bearing with an OD of 72 millimeter right in there, which would have an ID of probably about 30 millimeter or 35 millimeter. The OD on this is around 38 plus. I could turn this down, and because there's plenty of meat on this shaft right here, so I could take just a little bit off and get down to that size that I want to. So I definitely could do that. The real reason I'm hesitating to do that is because I'm not sure whether or not if I put a regular deep groove ball bearing in there, if it'll work. Now they have what's called an angular contact ball bearing. And the design, the way it's put together, is a little bit different. It's actually a little bit more like this. The way that this works. Similar. An angular contact ball bearing is able to take primarily a radial load, but it can also take axial loading to a certain extent. Better than a regular deep groove ball bearing. So I'm toying with the idea of putting one of those in there. But I was thinking about this, and I was just wondering what the heck were they thinking when they designed this to do that. This is a regular ball bearing. Okay, that's why I couldn't find it. I already had it on here. It's a regular deep groove ball bearing. So that ball bearing is designed to take the forces of this shaft as it's spinning. You know, the forces are going to be like this. It's not designed to take forces of it doing this. But it can't really do this if it's being held captive by this funky bearing assembly down below. So maybe that's why they only had to have it on the bottom. Now, what I think might be going on here is inside this hole there are two pins that stick out halfway into the bore. And what ends up happening is on the quill assembly, which I have not touched yet, other than to take it off the machine. So this is the drive shaft that goes down to the quill. And when I lower, if this is locked onto the column in a position that it's locked into, what happens is when I move this arm right here to lower and raise the quill as I'm drilling, it looks like by design this shaft is supposed to move in and out of here. So in other words, well, of course, now it doesn't want to go on. I probably damaged the edge of this when I was working on it. But once I clean this up, what's supposed to happen is this is supposed to slide up and down this shaft. Well, if I put it this way, let's see. I get to go on that way? Yeah, there we go. Yeah, because it's stopping right at the very end there, because at the very end is where I damaged it. All that crud that just came out of there. Anywho, this is going to have to be cleaned up and lubed. But there's your axial load. The axial load is that if as I'm lowering the quill while it's running, there's going to be a tendency for this shaft to be pulling down on this pulley. Okay? In other words, this is going to be running in here like this, and as I lower that quill and that shaft is coming down out of here, it's going to have a tendency to want to try and pull this down. So it's going to be putting that axial loading on there. Consequently, when I raise the quill back up, like when I'm pulling the drill out of a hole that I've drilled, it's going to have the effect of putting an axial load in the opposite direction. So the problem with angular contact ball bearings is the angular contact ball bearings are designed to take a radial load and an axial load in one direction only. If you have an application like mine where you might have loading in both directions, you're supposed to stack two of those bearings together. My problem with that is if I stack two of them together, they won't fit in this cup. And I can't make a taller cup and insert it in there, because then I run into a problem where I run out of room because this is right up against this bottom edge of this pulley. But I'm thinking now, the majority of the axial loading that's put on this bearing probably is really only occurring more on the plunge into, when I'm drilling. And because what's happening is when that drill is catching in that material, it's putting a drag or torque on this shaft, and since this pulley is turning and trying to turn it in the opposite direction that it wants to resist, it'll have the effect of keeping that on there tight, and that's why I think there's going to be more axial loading cutting or lowering the drill bit. Coming back out, it's always easier. Drill bit might be hanging up a little bit, but I think the axial loading will be minimal. So I think I am going to try and do an angular contact bearing in here. I'm probably going to ask for advice from the bearing guys before I do that. But right now that's what I'm leaning towards, so I just thought I'd let you know what I'm thinking. And as long as I'm talking radial and axial loads on bearings, I might as well mention one more time. I am going to modify this back bearing cup, which is basically this cup here. This is the one that had this funky deal in it here with this bushing type of bearing and an O-ring, and we know that's really sloppy. We know that the shaft that goes in here is pretty much just a tiny bit over 25 millimeters, so it should be a press fit into a 25 millimeter bearing race, which is great because I've already sourced a needle bearing. Needle bearings are roller bearings with very small diameter rollers in them, and they're ideal for supporting radial loads and not good for axial loads. Well, this back one here, we don't really have to worry about the axial load because that drive shaft goes down into the gearbox, and by design it's not really going to be putting any force up or down, pulling up and down on that pulley. So what I'm going to do is I'm going to have to modify this to accept the OD of that bearing. I forgot what it's going to be. One point when we were talking about it at the bearing place, he showed me the option of this bushing. This bushing right here, with just maybe taking a light skim cut inside here with the lathe, the boring bar, I should be able to push this bushing in there. And then the idea would be, depending on what my OD is on that needle bearing, I don't have it committed to memory, but that'll go in there like that. Then I wanted to have a way to keep, this is really going to be kind of upside down anyways, but just in case I have, want to keep dirt from getting into that bearing, because I'm going to have that bearing, it's going to be lubricated and put it in there. So just for the heck of it, it's cheap enough, I sourced an oil seal that fits nicely around that drive shaft, and that's going to be a press fit into here, and that'll protect that bearing that's going to go in there. So yeah, a little bit of overkill, but in for a penny, in for a pound. So I think I'm actually going to get this out of here, and maybe I'll revisit the gearbox. Last time we looked at the gearbox, I didn't have this stuff ready to go, and then I was talking about this groove. I ended up picking up an O-ring that will fit the OD of the shaft that goes through here nicely, and it'll also fill that groove. So once I pop that in there, a little bit of lubrication on the shaft will run in that O-ring. Ideally, I wanted a O-ring this size with a durometer rating of 90, which durometer rating is basically the hardness of the rubber and the abrasion resistance, because the problem is that by design this is probably not going to see a lot of oil. So over time it's going to wear this, but it's better than just having nothing in there at all, I think. This will keep dust and dirt from the outside shop environment from getting in there, and hopefully it'll also keep oil from trying to migrate along the shaft and come out and cause a drip. Of course, I'll know if it's a failure or a success after I've run this for a while. If I start to see oil dripping down here and staining this, then I'll know that that didn't work. And then, you know, maybe I could revisit the idea of modifying this to put a regular oil seal in here.